Crown ethers have been shown to form especially strong attractions to cationic metal atoms. So the metal atoms will actually sit right inside the crown ether, and since they're positively charged, they will interact very strongly with the negatively charged oxygens that also reside in the center of the crown ether. There are different sizes that have different names, and the names come from first the total number of atoms in the ring. So those are carbons plus oxygen. And also the second number comes from just the number of oxygen. Because there are multiple oxygens residing in the center, they form a very strong attraction to metals that have a positive charge. This is an electrostatic potential map for 18 crown 6, and it shows the red regions inside. Those are the regions that are particularly electron rich. And then the particularly electron poor regions are on the outside, all the way around. And so the negatively charged interior will fit a metal atom, right, such as potassium ion, which will fit nicely into 18 crown 6. Metal ions, right, such as potassium ions, are not going to be very soluble in low polarity solvents. And sometimes we need to use low polarity solvents in organic reactions because our organic reactants are going to be soluble in those lower polarity solvents. So they're ideal to dissolve the organic reactants, but our metal ions are not going to be very soluble. So if we add these crown ethers, they will complex to the metal cation, resulting in the complex, which is more soluble. So essentially, crown ethers are added to help ionic salts that are sometimes needed for organic reactions and help them dissolve in different lower polarity organic solvents. So for example, we might try to add potassium fluoride to a reaction because we would like to have fluoride act as a nucleophile in a reaction. But the problem is if we use benzene, which might otherwise be a great solvent, right, potassium fluoride will not be very soluble in benzene unless you add in the crown ether. So this is again 18 crown 6, and it's the perfect size to host the potassium ion because the potassium ion is very stable. It makes the entire thing, the potassium fluoride, more soluble in benzene. And if it's soluble, it can potentially react. So for example, perhaps we would want to do a nucleophilic substitution, an SN2 reaction with potassium fluoride, and we would need to use a low polarity solvent to dissolve up our organic substrate. We would not be able to get very much product from this reaction if we just rely on potassium fluoride's natural solubility in benzene. But if we then decide to add some 18 crown 6, all of a sudden solubility is enhanced, and therefore the amount of product we would be able to get increases. So which crown ether should you choose, right? It depends on the metal cation that you want to be soluble. So for example, if you're trying to solvate a lithium ion, you would choose 12 crown 4 because lithium will nicely fit inside the pocket for that size crown ether. If you're trying to solvate sodium ion, we need a slightly larger interior space because it's a larger metal ion, so we would choose 18 crown 5. And then the most common by far is 18 crown 6, which solvates potassium ions.